In this video, we would be talking about measurement and the metric system. For the metric system, it basically refers to the SI units, or in complete title, they're called the International Standard Units. Let's start. So, for measurement, it is the size of length or width, or in other words, it's called magnitude. In a particular sense, measurement needs to have a magnitude or a number. The act of determining size and capacity, and the most accurate definition for measurement among the rest is measurement is a comparison to a standard. You compare length or width or size and capacity to a specific standard. As for that standard, we will be mentioning about the specific units later. So, a measurement is not without a magnitude, as said earlier, and a unit. This definition earlier is half correct, since we also need a unit. Magnitude and unit perfectly defines what measurement is. So for magnitude, it's basically the number, and unit, it gives you the identity of a quantity, or how you call it as dimensions. For example, volume, you have liters; mass, you have grams; distance, kilometers, centimeter, meter, or even miles. But as for miles, we won't be involving that specific unit in this video. For time, we have seconds, minutes, hours. Temperature, if I'm not mistaken, there are only 3 specific temperature units: Celsius, Fahrenheit, and what's universally known as Kelvin. So what will be the standard? We'll be focusing more on the quantitative part of measurement, not the qualitative. I'm not sure if the qualitative is why we don't have qualitative is because in nature, measurement doesn't associate itself with qualitative data, or maybe for some other reason. But let's focus on the quantitative side. So we have 2 types. We have scalar and vector. For scalar, literally by the clue word scale, there is no direction. There is only a total journey. This is a scalar quantity is mostly used in chemistry topics, and for vector, it's mostly used for physics topics. Vector is, of course, with direction. So as you can see here, at the graphs below, for scalar, literally from the word scale, we can see a ruler here, a part of a traditional ruler, the normal ruler that we usually have at home or at school or at science laboratories. Under scalar topics, there are units such as distance, speed, temperature, volume, mass or weight, mole, and concentration. These are the covers of scalar quantity. There is no direction, only the total journey or the total quantity. Since in a specific context, total journey can only refer specifically to distance, speed, but as for the rest, they more associate themselves with quantity. Right. So for vector, as you can see here, the graphs, one is a Cartesian plane, since there is a referral to direction. As for force, these are the covers of vector. We have force, displacement, velocity, and acceleration. Everything here has direction. Force, we have weight, where is the weight going? Displacement, where is basically talks about the reference point. For velocity, it's speed with direction. Acceleration, that basically almost goes with the velocity, but in a different way, slightly different way. So you have to note this: mass and weight are different in the context of physics. So this is physics. it is reliant over vector. Why? Particularly for letter G, or the gravitational acceleration, if I'm not mistaken, it's 9.8 meters per second squared. This is this is a specific unit that is applied in physics. However, only in this world, on Earth. But in a different planet, your weight may vary, since the gravity force there is pretty different compared to Earth's. That's why in Mars or in space, I mean literally in Mars and in our own moon, the gravity is very different there. We levitate in some sense. And that's why we have to exercise more often in outer space, since we tend to lose a lot of muscle mass in the long term. So, for the metric system, or the SI unit, the International Standard Unit, we have 7 main SI units that represent the dimension that they are trying to measure. So first, we have Kelvin. Second, we have kilogram. Third, we have meter. Fourth, we have seconds. Fifth, we have mole or molecule. Sixth, we have ampere, which refers to electricity. And 7, candela, which refers to luminosity, or the intensity or brightness of the light. So, one thing that you also have to note about the quantities is that volume is equal to meter times meter times meter, or in other words, meter raised to 3. So, let's move on to the most common SI units. Let's tackle specific units that fall under their name. So for grams, we have kilograms, hectograms, decagram, grams, decigram, centigram, milligram, and skip 2 quantities over there, we get microgram. Skip another 2 quantities, we get nanogram. I'm not sure if your school has taught you about these 2 values, but generally most schools only focus on this part. They only focus from kilograms to all the way to milligram. But as for our school, we also have to think about a microgram and nanogram. They're just 2 values or 2 units apart from each other. So, as usual, for kilograms, this is our point of origin in a specific sense, since this is 1 times 1. And for decagram, we just times with 10 and times with 2 tens. And for kilograms, we times it with 3 tens, or in other words, 3 zeros. For the values below grams, decigram, centigram, and milligram, they're basically just 1 times 10. You just multiply times 10, 1 more in every step downwards. So 1 times 10, but the catch is, what makes it different from the upper values is that they have a raised to -1 exponent. Since it's basically the inverse. So imagine that this is sea level, and these are the above values, they're all positive, and the values below are negative, below sea level. So just think it that way if it is a lot more convenient to you, or you can always think about a different memory technique that you could apply to this so that you can remember the values and their corresponding formulas in a way. So for centigram, 1 times 10 times 10 raised to -1, which is basically 1 times 100 raised to -1. Milligram, that goes for the same, just add another 0 in multiplication. So for microgram, again, we skip 2 units, so we consider those 2 zeros. So from 1,000, we get 1 million. Since, for instance, we get 1,000, we get 2 more zeros. And as for microgram, we reached microgram, we get another 0. So that's how things work. Raised to negative 1, which is in other words a fraction if you could reciprocate it. And another 3 zeros, you get 1 billion for nanogram. Just always note that microgram is greater than nanogram. And as for the abbreviations, our science teacher, the teacher who taught us this, specifically noted that we're not advised to write the abbreviations of milligram and microgram, since no offense to those who couldn't write really properly or have a good or a decent penmanship when it comes to writing specific abbreviations, especially for doctors. This is the value for milligram, and this is the value for microgram. Some doctors tend to just make them the same in writing, and that's what we're trying to be careful about, since these two values are different. If the doctor prescribes a specific medicine for a patient in either milligrams or micrograms, for instance, you have to buy medicine at a pharmacy that is in milligrams, but then you thought it was micrograms, so that's a big no-no. That's a disaster. So let's move on to nanogram. We just acknowledged that nanogram has an abbreviation of NG, just in case you haven't been familiar with it yet. For decagram and decigram, the difference is that decagram decagram has a capital D, and decigram has a small d. Just associate capitalization with positive integers and decapitalization with negative integers. So let's move on to the second most common SI unit, which is liter. Ironically, liter is not an official SI unit, as stated earlier. You can see here that there is no liter here. However, it's still considered an international standard unit unofficially, for some awkward reason. Alright, so the same system goes with liters. You have kiloliter, hectoliter, decaliter, liter, deciliter, centiliter, milliliter. Skip 2 units, we got microliter, and another 2 units, we get nanoliter. Just note that as for liters, out of the 3, we have to capitalize liter for some reason, L. So the same thing goes with these values. 1 times 1000, 1 times 100, 1 times 10, 1 times 1. This is the base of reference. 1 times 10 raised to negative 1, 1 times 100 raised to negative 1, 1 times 1000 raised to negative 1. Add 3 more zeros, we get 1 million. 3 more zeros, for nanoliter, we get 1 billion. So I hope there's not much confusion here. They're literally the same with grams, but then, of course, what makes them different is the abbreviations and the specific values. So for meters, again, specific values are the same, but the labels are quite different in a way. What did not change here are the abbreviations, or in other words, the suffixes. We have kilo, hecto, deca, deci, centi, milli, micro, nano. So those are the suffixes. So for kilometer, we have km, 1 times 100, hecto, 1 times, kilo, we have 1 times 1000, hecto, 1 times 100, deca, 1 times 10, meter, 1 times 1, deci, 1 times 10 raised to negative 1, centi, 1 over 100, milli, 1 over 1000, micro, 1 over 1 million, and nano, 1 over 1 billion. So, actually these were supposed to be practice exercises, but not sure why there are answers already. But yeah, let me show you how I solved this. expect the next for the next video that it will be all about answering problems involving metric unit conversions. So these are giveaways. Consider these an opportunity to prepare for our review in the next video. So from 2 kilograms to centigrams, the first thing we need to do is that we have to count the zeros from kilograms to centigrams. So enlist a small table here. Kilogram to hectogram, 1, 2, 3, 4. I'm sorry. Let's repeat that. 1, 2, 3, 4, 5. We get 5 zeros. So 1 kilogram is then equal to 1, 2, 3, 4, 5 zeros centigram. After that, we just interchange their positions. The value on the left will be on the right. What's on the right will be on the left. So now we just place our denominator, since 100,000 over 1 is also equal to 100,000. So write it this way. 1 kilogram, of course, because it's already approved that 100,000 centigrams is equal to 1 kilogram. So write it this way, and it also these are options. This is option A, option B. Our objective, since we have the value of 2 kilogram to translate into centigram, we need to choose between these two fractions as to which is most likely to help in cancelling the current value, which is kilogram. So here we just write 2 kilogram over 1. Then since kilogram is in the numerator, we have to find the fraction with kilogram as denominator. As you can see here, this is what I encircled. Since kilogram is our denominator, place the fraction here, cancel the terms, and we get 200,000 centigrams. So this is the final answer. Let's move to number 2. 23.6 decagrams to decigrams. Let's find how many zeros there are far from each other. So DG to DG. I'm not sure how to distinct the two when it comes to saying them. So for 2 zeros, 1 DG is equal 1 decagram is equal to 1. Then 2 zeros, 100 decigrams. 100 decigrams equal to 1 decagram. Turn them into fractions. One and another. How do you make these fractions? Once you made the first one, you can just reciprocate to make the other one. So option A and B. Obviously, given 23.6 decagrams, decagrams is in the numerator, so we have to find the fraction wherein decagrams is in the denominator. So this is the one that we're looking for, option A. So cancel the terms, multiply them, we get 2,360 decigrams. For number 3, of course, we have to note, in general, our science teachers stated that fraction answers aren't appropriate as final answers. For instance, if a doctor gives you a paper enlisting what specific medicine and its specific unit, what you're supposed to buy at the pharmacy for the patient, fraction values aren't appropriate. What's more appropriate are decimals. So for number 3, 0.5 centigrams to hectograms. Actually, what we're doing right now, just to let you know, we're doing the long cut. We're doing the traditional, we're solving the traditional way. I'll be teaching you the shortcut way in the next video. Also within the video wherein we'll be practicing a lot. So, enlist the values here in grams. Hectogram, we still count downwards even if our value is from below to above. So kilogram to hectogram, 1, 2, 3, 4, 5. I'm sorry, wait, what? 1, 2, 3, 4, 5. Wait, I'm sorry. This is not from kilograms. It starts from hectograms. 1, 2, 3, 4. So we get 4 zeros. 1 hectogram is equal to 10,000 centigrams. 1, 2, 3, 4. We just write the zeros, turn them into fractions, and make option A and option B. What's most appropriate? This fraction over here, option A. Cancel the terms, you get this one. Turn them into, usually the calculator would say this as an answer. It is in, if I'm not wrong, it's called scientific notation. But then you could it's more appropriate to write the final answer in decimals, or you can just write 5 times 10 raised to negative 5 hg. In algebra, it is advised by teachers, it is advised for you to not use x as a sign for multiplication. For example, 5 times 4 equal to 20, because that might be in the algebraic context, it might be like this, which is a lot entirely different compared to this. But in the context of physics, or in specifically in the world of metric unit conversion, x as multiplication is pretty tolerated. It's accepted. So this is something that we don't appreciate in metric unit conversion. This is something that we usually do in algebra, right? So yeah. Let's move to number 4. 2 decagrams, 2 decigrams. From decagrams, we get 2 zeros in total. So 1 decagram to decigram is equivalent to 100 decigrams. Interchange the values, make the fractions option A, option B. So cancel the terms, and we get 200 decigrams. So that's it. You don't have anything else in this lecture. This is everything that you have to know. Alright. Thanks for watching. I'll see you in the next video.